Here we are again, you and I, back in our quiet room with the lamp burning steadily on the table. The light falls the same way it always does, warm and golden against the pages of our book. The chair beneath you holds your weight with familiar patience. Outside the window, the darkness is complete and gentle, the kind of deep quiet that comes late at night when the world has settled into rest. This is our place. This lamp, this table, this corner of the house where we've been reading together for several nights now. There's comfort in returning here, in finding everything just as we left it. The book still open to where we paused, the blanket within reach if you want it, the sense that we can take all the time we need. We've been reading through this book together for a few nights now. We noticed blank pages scattered through the text, places where something invisible seemed to be written. We confirmed that this invisible writing has weight and presence, that it shapes the way galaxies move and hold together. We looked at a few candidates for what that invisible ink might say, what kind of matter might be filling those blank spaces. Tonight, we turn to a different kind of chapter, not about what fills the blank pages, but about what the pages themselves are doing. The book we're reading, it turns out, is slowly expanding. The pages are stretching, growing larger in a way that's gentle and persistent. And stranger still, that stretching seems to be getting faster with time. This isn't about dark matter anymore. Dark matter is the invisible scaffolding, the structure that holds galaxies together. What we're turning toward now is something else, something that works in the opposite direction. Where dark matter pulls inward through gravity, this other presence pushes outward, making space itself grow larger. We call it dark energy. And tonight, we're going to look at how we discovered it, what it seems to be doing, and why it remains one of the deepest mysteries we've encountered. Let's set our intention for this chapter before we begin. We're not here to solve this mystery tonight. We're here to sit with it, to understand what we've learned so far and what remains uncertain. This is one of those questions where the discovery itself feels almost impossible, where the evidence pointed towards something so unexpected that it took years for researchers to trust what they were seeing. The universe is stretching. That much we've known for about a century. But the stretching isn't slowing down the way gravity would suggest. It's speeding up. Something is gently, persistently pushing outward, and we don't yet know what it is. That might sound unsettling, but here by the lamp, we can approach it differently. We can treat this as an invitation rather than a void, as a place where our understanding opens rather than closes. Think about what it means to realize that the pages themselves are changing. Not the words we're reading, not the content of the text, but the medium itself. The paper stretching beneath the ink. The chapters growing longer without any new sentences being added. It's a strange realization, the kind that makes you look at the book differently, makes you notice something fundamental that you'd taken for granted. We assume the pages stay the same size. We assume the structure is stable, unchanging, a reliable foundation for whatever story is written there. But what if it isn't? What if the pages have been quietly, patiently expanding all along, and we only just noticed? The universe, as far as current evidence tells us, is vast and ancient and patient. It's been stretching for billions of years. There's no urgency in that stretching, no crisis, just a slow and steady change that we can trace backward and this chapter one page at a time. We'll look at the evidence carefully. We'll acknowledge what we know and what we don't know. And at the end, we'll set the chapter down gently on the table beside the others. Another piece of the larger story we're building together. Let that intention settle for a moment. We're not rushing anywhere. The lamp will keep burning. The chair will keep holding you. We have all the time we need. For now, let's turn the page and step into the first room. Before we can understand what dark energy does, we need to be clear about what cosmic expansion actually is. It's easy to picture it wrong. You might imagine everything flying outward from some central point, like debris scattered across a room. But that's not quite right. Expansion isn't things moving through space. It's space itself stretching. Every part of space in all directions at once, growing gradually larger. Imagine our house, the quiet structure we've been sitting in all season. Now imagine that the rooms themselves are growing, not the furniture moving apart, but the walls gently stretching outward, making each room a little larger with time. A chair in one corner and a lamp in another don't move closer to the walls move away from them. The distance between any two objects in the room grows, not because anything is traveling, but because the room itself is expanding. What would that feel like if you were standing in such a room? You might not notice it at all at first. The change would be so gradual, so patient, that nothing in your immediate experience would seem different. The chair would still feel solid beneath you. The lamp would still cast the same warm circle of light. But if you measured carefully, if you marked the distance from one wall to another and came back later to measure again, you'd find that the room had grown. Not by much, just a little, but measurably, undeniably larger. And if you measured the distance to very distant rooms in the house, rooms far down long hallways, you'd notice something else. The farther away a room was, the faster it seemed to be receding. Not because those distant rooms were moving faster through the house, but because there was more space between you and them. And all of that space was stretching. That's what's happening to the universe. The fabric of space is stretching. Galaxies aren't racing through space away from each other. The space between them is growing. This idea took shape in the early 20th century. Edwin Hubble, working at Mount Wilson Observatory in 1929, measured the light from distant galaxies and noticed something consistent. The farther away a galaxy was, the more its light was shifted toward the red end of the spectrum. This red shift, as we call it, happens when the source of light is moving away from us, or, more accurately, when the space between us and the source is stretching. A Belgian physicist and priest named Georges Lemaitre had already proposed, based on Einstein's equations, that the universe might be expanding. Hubble's observations gave that proposal solid ground to stand on. So by the early 1930s, the picture had changed. The universe wasn't static and eternal. It was dynamic, stretching, evolving. The distant galaxies were drifting farther apart because the space between them was growing. Back here by the lamp, we can rest that foundation on the table. The universe is expanding. That's been part of our understanding for nearly a century. Let it settle there for a moment, a cornerstone of everything that follows. What we didn't know, what wouldn't become clear for decades more, was whether that expansion would continue forever, whether it was slowing down, or whether something else entirely was happening. To answer that question, astronomers needed a way to measure cosmic distances with precision. If you want to know how fast the universe is expanding, you need to know how far away things are and how fast they're moving. The motion part is relatively straightforward. You measure the redshift of a galaxy's light, and that tells you how much the space between you and that galaxy has stretched. But distance is harder. You can't just look at a galaxy and know how far away it is. A dim galaxy might be nearby and faint, or it might be distant and bright. You need some kind of reference, some object whose true brightness you know, so you can compare that to how bright it appears and calculate the distance. We call these objects standard candles. Think of a lamp in a hallway. If you know how bright the lamp actually is, you can judge how far away it is by how dim it looks from where you're standing. A lamp at the end of a long hallway looks fainter than the same lamp held close. This is something we understand intuitively. Brightness and distance have a relationship we can feel. When you see a light in the distance, part of your mind is already calculating how far away it must be based on how bright it appears. The dimmer the light, the farther the hallway must extend. It's a simple principle, but applying it to cosmic distances requires finding objects that are bright enough to be seen across billions of light years, and consistent enough that we can trust their luminosity. In the 1990s, astronomers realized they had a remarkably good standard candle, a specific type of stellar event called a Type 1a supernova. These events happen when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star. When the white dwarf's mass reaches a critical threshold, about 1.4 times the mass of our Sun, something dramatic happens. The star can no longer support itself, and it undergoes a runaway process that releases an enormous amount of light. This threshold, called the Chandrasekhar limit, is based on fundamental physics. It's the same everywhere in the universe. And because Type 1a supernovae all reach roughly the same mass before they brighten, they all reach roughly the same peak luminosity. That makes them extraordinarily useful. When we see a Type 1a supernova in a distant galaxy, we know roughly how bright it should be at its peak. By measuring how bright it actually appears, we can calculate how far away it is. It's like having a lamp of known brightness that we can place in distant rooms throughout the house, measuring how the light dims with distance, mapping the size and shape of the structure around us. Let that settle for a moment. We have a tool, a way to measure vast distances with reasonable precision. A lamp we can see even when it's very far down the hallway. In the mid-1990s, two groups of astronomers, working independently, began using Type 1a supernovae to map the history of cosmic expansion. One group, called the Supernova Cosmology Project, was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other, called the High Z Supernova Search Team, was led by Brian Schmidt, working in Australia, and included Adam Rees among its key members. Both teams had the same goal. They wanted to measure how much the universe's expansion had slowed over cosmic time. The expectation was clear. The universe is filled with matter, and matter pulls things together through gravity. So the expansion should have been faster in the distant past and slower now. The question was, how much slower? That would tell us whether the universe would keep expanding forever, just more and more gradually, or whether gravity would eventually pull everything back together. This wasn't a question with an uncertain answer. It seemed straightforward. We knew the universe was expanding. We knew it contained matter. We knew matter creates gravity. The conclusion felt inevitable. The expansion must be decelerating. The only question was the rate. How much had it slowed? Was it slowing fast enough that the expansion would eventually stop and reverse? Or was it slowing more gently, coasting toward an eternal but ever slower expansion? It was a question you could set out to answer with confidence. The framework was solid. The physics was well understood. The measurements would be difficult, requiring extraordinary precision and care. But the question itself seemed well posed. They spent years developing techniques, finding supernovae, measuring their distances and redshifts, refining their methods. It was painstaking work, careful and methodical, like slowly turning pages in a very long book, checking each one for subtle patterns. What they found, when the data finally came together in 1998, was something neither team expected. The universe's expansion wasn't slowing down. It was speeding up. Both teams arrived at this conclusion independently. They checked their data, looked for errors, tested alternative explanations. The result held. For this discovery, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. Back here by the lamp, we can set that discovery on the table and let it rest for a moment. The careful expectation, the years of painstaking work, and then the data saying something completely different from what the questions had been designed to find. It's one of those findings that feels quiet at first, almost understated, until you sit with it for a while and realize what it means. If the expansion is accelerating, then something we hadn't accounted for must be pushing outward, working against gravity. Let's turn the page and look at that moment more closely. When the data from those distant supernovae came in, both teams noticed the same thing. The supernovae were dimmer than expected, not by much, but consistently across multiple observations. About 20 to 25% dimmer than the models predicted. That meant they were farther away than they should have been. Let's sit with that for a moment. If a lamp in the hallway looks dimmer than expected, it means the hallway is longer than you thought. The light has traveled farther, and so it appears fainter. You stand in the doorway, looking down the corridor. You know how bright that lamp should appear, based on where you think it's placed. But it looks dimmer. Your first thought might be that the lamp itself is different, or that something is blocking the light. But if you check carefully and find that the lamp is exactly what you expected, and nothing is in the way, then you have to consider another possibility. The hallway is longer than you measured. The space between you and the lamp has somehow grown. The lamp hasn't moved, but the distance has increased. That's what the supernova data was saying. In cosmic terms, if the distant supernovae were farther away than expected, it meant the universe had expanded more than it should have over the time since those supernovae occurred. The stretching had been faster than the models predicted. And if the stretching had been faster, that meant the expansion wasn't slowing down under gravity's pull. It was speeding up. Both teams ran systematic checks. They looked for dust that might be dimming the light. They examined whether the supernovae themselves might be intrinsically fainter in the distant past. They tested whether their distance measurements might be off. They compared their calibrations, their methods, their assumptions. The conclusion held. The supernovae really were farther away than expected. The expansion really was accelerating, And here's what made the result credible. Both teams found the same thing, independently, working with different approaches, different observing strategies, different analysis methods. They weren't collaborating. They didn't know what the other group was finding until the results were nearly complete. Two separate groups asking the same question, using the same kind of evidence, arriving at the same unexpected answer. That's what science looks for. Not just one surprising result, but independent confirmation. It was one of those moments in science where the data says something clear and surprising, and you have to decide whether to trust it. Both teams trusted it. And the announcement in 1998 changed the entire chapter. Let's imagine tossing a ball gently upward. Gravity pulls the ball downward, slowing its ascent. You expect it to rise quickly at first, then more slowly, then stop and fall back down. The ball's speed decreases over time because gravity is working against its motion. That's what we expected for the universe's expansion. Matter creates gravity, and gravity pulls things together, so the expansion should slow over time. The question was whether it would slow enough to eventually reverse, or whether it would keep going forever, just more and more gradually. But what the supernova data showed was the equivalent of tossing a ball upward and watching it rise faster and faster instead of slower. The speed increasing rather than decreasing. The sign was wrong. Something was pushing outward, gently and persistently, working against gravity's inward pull. For the scientific community, this was a moment of quiet recalibration. Not panic, not alarm, but a willingness to let the evidence reshape the story. The framework that had seemed so solid, the expectation of deceleration, had to be set aside. This is what science does at its best. It remains open to being surprised. It builds careful expectations based on the best available understanding, and then it's willing to revise those expectations when the data points elsewhere. Back here by the lamp, we can acknowledge that this was deeply unexpected. The equations didn't predict it, the models didn't require it, and yet the evidence pointed clearly toward it. The discovery from the two supernova teams was remarkable, but it was also so unexpected that researchers needed independent confirmation. That confirmation came from multiple directions over the following years. One line of evidence came from studying the cosmic microwave background, the faint afterglow of the hot, dense state the universe was in about 13 billion years ago. This light carries patterns, subtle variations in temperature that encode information about the universe's composition and geometry. Two space missions, WMAP launched in 2001 and Planck launched in 2009, mapped these patterns with extraordinary precision. What they found was that the universe is spatially flat, not curved inward like the surface of a sphere, not curved outward like a saddle, but flat, like the pages of a book laid open on the table. Let that observation rest for a moment. Flatness. It sounds simple, but it has implications. That flatness has a specific meaning. If you add up all the energy in the universe, the total should equal a specific critical density. WMAP and Planck measurements showed that ordinary matter and dark matter together make up only about 31 to 32% of that total. The rest, about 68 to 69%, had to be something else. Something that didn't behave like matter. Something consistent with the accelerating expansion the supernova teams had found. Another line of evidence came from studying patterns in how galaxies are distributed across space. In the early universe, sound waves traveled through the hot plasma before atoms formed. When atoms finally did form, those sound waves froze in place, creating a characteristic scale, a preferred distance of about 490 million light-years, where galaxies would later tend to cluster. We call these patterns baryon acoustic oscillations. They act as a kind of standard ruler, a known distance we can use to map cosmic expansion at different times. Large galaxy surveys measured these patterns and found the same thing the supernovae had shown. The expansion was accelerating. So by the mid-2000s, we had three independent methods. Three different ways of looking at the universe. Each one could have disagreed with the others. Each one could have pointed in a different direction, forcing us to choose which to trust, or to acknowledge that we didn't understand something fundamental. But they didn't disagree. They converged. Supernovae said the expansion is accelerating. The cosmic microwave background said there's energy we haven't accounted for. Galaxy clustering said the same thing from yet another angle. Three lines of evidence, all pointing toward the same conclusion. The expansion is speeding up. Something we call dark energy, for lack of a better name, makes up about 2/3 of the universe's total energy content. The data converged. The story had to change. Back here by the lamp, we can set those three lines of evidence on the table, side by side. Supernovae, the cosmic microwave background, galaxy clustering, all of them saying the same thing, each one strengthening the others. Let's rest here for a moment before we ask the next question. What is this dark energy? What could possibly cause the universe to stretch faster over time? To understand one possible answer, we need to go back about a century, to a time before we knew the universe was expanding at all. Albert Einstein, working through his new theory of gravity in 1915 and 1916, found something troubling. His equations suggested that the universe couldn't simply sit still. Gravity would pull everything together, collapsing the whole structure inward. But astronomers at the time saw a cosmos that seemed stable, eternal, unchanging. So in 1917, Einstein added a term to his equations. He called it the cosmological constant, usually written as the Greek letter lambda. It represented a kind of gentle outward pressure built into space itself, a way to balance gravity's inward pull and keep the universe steady. It seemed like a reasonable adjustment, a small mathematical note to make the theory match what was observed. But within a few years, as we discussed earlier, evidence began to suggest the universe wasn't static at all. Lemaitre proposed expansion based on the equations. Hubble observed it in the motion of distant galaxies. If the universe was expanding anyway, there was no need for that extra term. Einstein, according to accounts from physicist George Gamow, later referred to the cosmological constant as his biggest blunder. So lambda was set aside, left on a shelf like a book we thought we'd finished with. For decades it seemed like a discarded idea, a mistake, a mathematical artifact that didn't correspond to anything real. But after 1998, when the evidence for accelerating expansion became clear, researchers realized they might need to take that book off the shelf again. The simplest explanation for dark energy is that Einstein's cosmological constant is real. Not a mistake, but a fundamental property of space itself. In this view, Dark energy isn't a substance or a field that moves or changes. It's woven into the structure of space, like energy embedded in the walls of our house. Every cubic meter of empty space carries a tiny amount of this energy. And as the universe expands, creating more space, there's more total energy pushing outward. More wall means more wall energy. More space means more dark energy. That's why the acceleration can continue, even grow stronger over time. Think about what that means. The rooms in our house are growing. As they grow, the walls stretch. And as the walls stretch, they carry more of this energy with them. The energy isn't added from somewhere else. It's not flowing in from outside. It's intrinsic to the walls themselves. More wall, more energy. It's an elegant idea, simple in its mathematics, consistent with the observations, and remarkably minimal in its assumptions. Let that image settle. The walls of space carrying their own gentle outward pressure, not violently, not dramatically, but patiently and persistently, making the rooms grow. But it comes with a deep puzzle. When physicists try to calculate what the cosmological constant should be, using quantum field theory, they run into a problem. The calculation gives a number, but that number is wrong. Not a little bit wrong. Not off by a factor of 2 or 10 or even a million. The theoretical prediction is larger than the observed value by a factor of about 10 to the power of 120. That's a 1, followed by 120 zeros. It's one of the largest discrepancies between theory and observation in all of physics. Imagine it this way. The mathematics says the walls should be vibrating with enormous energy, enough to make the entire house unrecognizable, unstable, completely unlike what we observe. But when we measure the walls, we find them almost perfectly still. Just the tiniest, gentlest pressure, barely there at all. We don't know why this is. We don't know if there's some mechanism that cancels out most of the vacuum energy, leaving only the tiny amount we observe. We don't know if our theoretical framework is missing something fundamental. We don't know if the question itself is being asked correctly. It's a puzzle that remains open. We can acknowledge it without forcing a resolution. We can set it on the shelf as a question we haven't answered yet, a place where the chapter still has blank pages. What we can say is this: the observed value of the cosmological constant, whatever its origin, is very small but not zero. And that small value is enough to make the universe's expansion accelerate. Let's step back and look at the whole picture, the model that's emerged from all this evidence. We call it Lambda-CDM. Lambda for the cosmological constant, representing dark energy. CDM for cold dark matter, the invisible scaffolding we discussed in previous chapters. Based on current evidence, the universe's total energy content divides roughly like this: about 68% dark energy, about 27% dark matter, and about 5% ordinary matter. That ordinary matter includes everything we can see and touch: stars, planets, gas clouds, galaxies. You and I sitting here by the lamp. It's a small fraction of the total. Dark matter is the structure that holds galaxies together, the invisible weight that shapes how matter clumps and clusters. Dark energy is the gentle outward push that makes space stretch faster over time. Together, they make up about 95% of everything. The missing 95% that gives this season its name. This model, Lambda-CDM fits the data we have remarkably well. The observations from supernovae, from the cosmic microwave background, from galaxy surveys, from gravitational lensing, all of it fits together into a coherent picture. Does that mean the model is final, complete, the last word? No, science doesn't work that way. Models are tools, maps, ways of organizing what we know. They're useful when they fit the evidence and make accurate predictions. And Lambda-CDM does both of those things. But we also have to be honest about what we don't understand. We don't know why the cosmological constant has the value it does. We don't know if it's truly constant, or if it might change slowly over cosmic time in ways we haven't detected yet. We don't know what dark matter is made of. Think about what it means to work with a model you know is incomplete. It's not a failure. It's the nature of understanding itself. We build the best framework we can with the evidence available. We use it to make predictions, to guide observations, to organize our thinking, and we remain ready to revise it when new evidence arrives. That's the position we're in now. Lambda-CDM works. It fits what we see. It's the best map we have. But we know there are territories on that map marked with uncertainty, places where the details remain unclear. The model works. It organizes the evidence. It makes predictions that we can test. But there are still blank pages, still questions resting in the margins. Back here by the lamp, we can accept that. We can hold both things at once, a model that fits the data well, and an acknowledgement of what remains uncertain. Let's turn to one more puzzle before we close this chapter. There's a number at the heart of cosmic expansion, a measure of how fast the universe is stretching right now. We call it the Hubble constant, named after Edwin Hubble, and we write it as H0. It tells us how much faster distant galaxies are receding for every additional megaparsec of distance between us and them. You'd think measuring this number would be straightforward. After all, we've been studying cosmic expansion for nearly a century. We have multiple methods, sophisticated instruments, careful observations. But here's the puzzle. We have two primary ways of measuring H0, and they give us two different answers. One method looks at the early universe. We study the cosmic microwave background, that faint afterglow from when the universe was about 380,000 years old. From the patterns in that ancient light, using our best models of how the universe evolves, we can calculate what the expansion rate should be today. It's like measuring the rooms in our house by looking at the original blueprints, the plans from when the structure was first built. You can see the dimensions as they were drawn. You understand the construction principles, how the house was meant to be built. And from those blueprints, you calculate forward. If the house was built according to plan, if it's aged and settled in predictable ways, then the room should be this size now. The other method looks at the nearby universe. We measure distances to objects like Cepheid variable stars and Type 1a supernovae, building a distance ladder step by step, and we calculate the expansion rate directly from the motion we observe. It's like measuring the rooms with a tape, moving from one reference point to the next, determining the size of the house as it exists right now. You start with nearby objects, whose distances you can measure reliably. You use those to calibrate the next rung of the ladder. Step by step, you extend your measurements farther and farther until you can map the expansion directly. Both approaches are careful. Both are based on solid physics. Both have been refined over years of work by multiple independent teams, and you'd expect them to agree. The blueprint should match the tape measurements. The calculation from the early universe should give you the same answer as a direct observation of the nearby universe. But they don't agree. And that disagreement creates a quiet unease, a sense that something in our understanding might need adjustment. The early universe method, using data from the Planck satellite and our best cosmological models, gives us a Hubble constant of about 67.4 kilometers per second per megaparsec. The nearby universe method, using observations of Cepheid stars and supernovae, calibrated with data from the Hubble Space Telescope, and more recently from the James Webb Space Telescope, gives us a value closer to 73 kilometers per second per megaparsec. That's a difference of about 8%. It might not sound like much, but in cosmology, where measurements are made with extraordinary precision, it's significant. The statistical significance of this disagreement is greater than 5 sigma. In the language of physics, that means the probability of this being just a random fluctuation, just bad luck in how the measurements happen to come out, is extraordinarily small, less than 1 in a few million. This isn't a marginal difference that might go away with more careful work. This is a substantial disagreement that's been confirmed and sharpened over years of increasingly precise observations. The James Webb Space Telescope, with its remarkable sensitivity, has confirmed the accuracy of the nearby universe measurements. The Cepheid distances, the calibration of the distance ladder, those appear to be solid. The systematic errors that researchers worried about, the subtle effects that could throw off the measurements, those have been checked and rechecked. So the tension isn't going away. If anything, it's sharpening. The more carefully we measure, the clearer the disagreement becomes. Back here by the lamp, we can acknowledge that this is genuinely puzzling. 2 careful methods, both based on sound principles, both refined by skilled researchers, and yet they give different answers. We call this the Hubble tension. It's one of those places where the chapter is still being written. If the tension is real, if it's not just some subtle error we haven't found yet, it could be pointing towards something new. One possibility is that dark energy behaves differently than we think. Perhaps it's not truly constant. Perhaps it has changed over cosmic time in ways our current models don't account for. That would affect how we calculate the expansion rate from early universe data. The blueprints would need revision. The assumptions we make about how the house ages, how the rooms grow over time, those might need adjustment. Or perhaps there's something about the early universe itself that we've misunderstood. Some component or interaction that affects the cosmic microwave background, but doesn't show up in nearby measurements. Or maybe our understanding of cosmic distances needs refinement. These are difficult observations, pushing the limits of what our instruments can do. Even small systematic effects can shift the results. Researchers are working on this from multiple angles. New observations, independent checks, alternative methods. The goal is to either resolve the tension or confirm that it's telling us something genuinely new about how the universe works. And here's what this tension means for the larger story we've been building this season. The missing 95% keeps surprising us. We thought we understood dark matter well enough to map its distribution. We're still looking for what it's made of. We thought we understood dark energy as a simple cosmological constant. now we have a tension that might be suggesting it's more complicated. Even our best model, Lambda-CDM, the framework that fits so much of the data so well, has this unresolved thread running through it. This place where the measurements don't quite agree, where the story might need another revision. For now, we can leave this question resting on the shelf. It's an invitation, not a conclusion. A place where the evidence is pointing towards something we don't fully understand yet. We don't need to force an answer tonight. We can acknowledge the tension, note what it might mean, and keep reading. Back here by the lamp, we can rest with that uncertainty. It's one more blank page in the book, one more place where the chapter opens rather than closes. And that's all right. That's how understanding grows. Not by filling every page at once, but by noticing where the blank spaces are and being patient with them. Let's gather the pages we've turned tonight and see how they fit together. We began with the discovery that the universe is expanding. That realization, which took shape nearly a century ago, changed our picture of the cosmos from something static and eternal to something dynamic and evolving. We saw how astronomers developed ways to measure that expansion with precision, using Type 1a supernovae as standard candles, lamps of known brightness placed in distant rooms throughout the cosmic structure. We looked at the work of two independent teams, Saul Perlmutter's Supernova Cosmology project and Brian Schmidt and Adam Rees's High-Z team, who both discovered in 1998 that the expansion isn't slowing down, but speeding up. Something is pushing outward, gently and persistently, against the inward pull of gravity. We saw how that discovery was confirmed through multiple independent methods. The cosmic microwave background showed us that the universe is flat, and that matter alone can't account for its total energy content. Patterns in galaxy clustering provided another line of evidence pointing toward the same conclusion. We explored what dark energy might be. The simplest possibility is Einstein's cosmological constant, resurrected after decades on the shelf. A property of space itself, energy woven into the walls of the universe. More space, meaning more energy. We acknowledged the vacuum energy problem, that vast mismatch between theoretical prediction and observed value. A puzzle that remains open, a question we haven't resolved. And we looked at the Hubble tension, the disagreement between two careful methods for measuring the current expansion rate. A place where the evidence might be pointing towards something new, something we don't yet understand about how the universe evolves. These aren't neat answers. They're more like open doorways, thresholds where one chapter ends and another begins. Let's step back further and see where we've been across these 4 nights. We began this season by noticing the blank pages scattered through our book. Pages where something invisible seemed to be written. We called them the missing 95%, the vast majority of the universe's content that we can't see directly. In the first episode, we asked whether those blank pages were really there, or whether we might be misreading the text. We looked at the evidence for dark matter and found it remarkably strong, woven through multiple observations from galaxy rotation curves to gravitational lensing to the cosmic microwave background. In the second episode, we confirmed that something invisible is written on those pages. We saw how dark matter shapes the formation of cosmic structure, how it acts as scaffolding around which galaxies and clusters can form and grow. In the third episode, we looked at candidates for what that invisible ink might say. What is dark matter made of? We examined several possibilities, from WIMPs to axions to primordial black holes and found that the question remains open. Tonight, we discovered that the blank pages aren't just blank. They're expanding. The book itself is growing, the pages stretching gently outward. And that stretching is getting faster with time. The missing 95% isn't passive or inert. It's active. Dark matter pulls things together, shaping structure. Dark energy pushes things apart, making space itself grow. Together, they define how the universe evolves over cosmic time, how galaxies form and cluster, how the expansion proceeds, how the future might unfold. In the chapters ahead, we'll continue turning these pages. We'll look at how researchers are trying to map dark energy more precisely, to test whether it's truly constant or whether it might be something more dynamic. We'll consider what the long-term future might hold for a universe that's accelerating outward. But that's for another night. For now, we've turned enough pages. Let's set this chapter down gently on the table beside the others. The universe is stretching. That's what tonight's reading tells us. Not violently, not urgently, but with a patient and persistent pressure that's been building for billions of years. Something we call dark energy, whether it's the cosmological constant or something more subtle, is gently pushing outward, working against gravity, making the space between distant galaxies grow a little faster with each passing moment. We don't fully understand it. We don't know why it has the value it does, or whether it will remain constant forever, or what it means for the long-term future of everything. But we know it's there. The evidence is clear and consistent and convergent. Multiple lines of observation, independent methods, all pointing toward the same conclusion. That's enough for tonight. We don't need to resolve every question. We don't need to turn every blank page into filled text. We can leave some questions resting in the margins, acknowledging what we know and what we don't know, holding both with the same patient attention we've brought to everything else in this season. The lamp is still burning. The chair is still steady beneath us. The window shows the same quiet darkness it always has. And the book is still here, waiting for us to turn the next page, whenever we choose. Rest well.